We can see interpretations of partial derivatives in many contexts, including some in physics/chemistry, as the example here will show, looking at the ideal gas law. Here we're going to be considering pressure as an output and the volume and temperature of a gas as the inputs. And the ideal gas law gives this relationship here. We're going to assume that we're working with 1 mole of the gas and that we're working with our standard constant with the units, traditional units of 8.31 for this R. And so what we see is the two variables, temperature and volume, and the constants over here, the N and the R. With this formula, we can very directly find the partial derivatives of P with respect to V and P with respect to T. Let's write first our function in more explicit terms with powers, because it's easier to differentiate powers. So pressure is equal to the number of moles. Well, that's going to be 1 for us. So number of moles, we'll leave the R in rather than putting 8.31 everywhere. Temperature to the power 1 and volume to the power -1. As soon as we write the formula that way, we can find the partial derivatives fairly easily. T is the variable, or we consider that to be the variable. R and V are constants, and so the derivative just makes the T disappear. And we would usually write that as R over V. And the other derivative, the other partial derivative, with respect to volume, would be R and T are constants, and the derivative of V to the -1 is of course V to the -2 with a -1 out front. And that would be negative RT over V squared. So that would be a traditional calculation of a partial derivative and the other partial derivative based on a formula. We can evaluate that at some reasonable numbers, so 300 kelvins, roughly room temperature, volume of 10 liters. We start working with that, we can see what kind of values we get. We also have R equals 8.31. So with those values in mind, we can find the temperature derivative the most easily, because it was simply R over V. And so it was 8.31 over 10. That gives us 0.831, and the units there would be kilopascals per degree Kelvin, if you work out through all the units. Or you look back here and say what units of pressure are natural with, or go with the constant we've picked here. That's kilopascals, and temperature degrees Kelvin. The other partial derivative we can evaluate as well with respect to volume. That was minus RT over V squared. And plugging in our values here, we get negative 8.31 times the 300 Kelvin divided by our volume squared. And that ends up being basically 3 times 8, or let's call it roughly negative 24. Units this time, kilopascals per unit of volume. So go back right to the derivative we're evaluating here. Kilopascals per liter. And so evaluating these partial derivatives is straightforward as well. And last but not least, we want to look at the interpretation of both of those numbers. What do those values mean? Well, if we have that our derivative, partial derivative of pressure with respect to temperature is 0.831 kilopascals per degree Kelvin at temperature 300 and at volume 10 liters. We have to be somewhere to get this value here, and once we're at that condition or at that point, then the evaluation is simply that for each increase, again, always increase in the inputs, increase in the temperature, so notice the per degree Kelvin here, we expect the pressure to increase by 0.831 kilopascals. So literally taking that 0.8 kilopascals per degree Kelvin, for each degree Kelvin, we expect the kilopascals to go up by 0.831. And following exactly the same logic, except with a negative value. Turns out we're at 24.9 here. Kilopascals per liter. Again, at a specific point, this value here came from the temperature being 300 and volume being 10 liters. Then for each increase in the volume of 1 liter, we expect the pressure to increase. Oh wait, do we expect the pressure to increase? Wait, the derivative is negative, which means when P goes up, or volume goes up, the pressure is going to go down. So we expect the pressure to decrease by 24.9 kilopascals when we increase by the volume by 1 liter. And that's an important distinction here. You can look at some of the scale effects and ask yourself if they make sense. In a 10-liter container, changing things by 1 liter is a pretty dramatic change, and so the pressure should consequently change by a fair bit, especially relative to a 1 degree change. Going from 300 to 301 Kelvin shouldn't have that much influence on the overall pressure in a container. And so we see the scale as well as the sign of these derivatives matching our expectations or our intuition about the physical scenario.